This is a modern factory, made up of dozens of autonomous industrial robots working together to assemble a car. This type of assembly line often takes less than 30 hours to assemble an entire modern car from scratch, with little human intervention during the process. Tesla's Gigafactory, for example, takes less than 10 hours to assemble a Tesla Model Y completely from scratch. It's something impressive, especially because in this estimated 10-hour period, about 570 cars are completed. It's an efficient, automated, and highly profitable industry worth over $250 billion. That's where Machine Labs comes in, a company founded by a former SpaceX employee, bringing a new approach that's completely different from how the industries of the future should be. Using the roboforming technique, Machine Labs manufactures any type of metal part for industrial use with just two things: a lot of artificial intelligence and two industrial robots working in sync. The difference here is that instead of pressing, as is literally done in all modern factories today, Machine Labs robots stretch the part in a different way until it reaches the desired shape, a process that takes a few minutes or several dozen hours, depending on the part. But how exactly is roboforming better than conventional forming? And why is it the future? Well, at the beginning of the automotive industry, many parts were forged and hammered manually by skilled craftsmen until they reached the desired shape. This included everything from building the bodywork, structural components, to ornamental details. Blacksmiths and metalworkers shaped the steel or iron using anvils, hammers, and forges to form the parts. This process was time-consuming and required a lot of skill, but it allowed for detailed customization. Moving forward in time, the bump forming technique became part of the process, which is actually still used to this day. Bump forming is a metal forming process used to create complex shapes and precise curves in sheet metal parts. This method is especially useful for producing components with complicated geometries, or that require multiple bends without seams. In bump forming, the sheet metal is manipulated using a series of controlled strikes or pushes applied by a tool. These strikes are applied precisely and sequentially along the sheet to gradually bend it into the desired shape. The tool can be a hammer, a press, or a computer numerical control machine, depending on the required precision and the complexity of the part. This process is often used in the manufacturing of small and large metal structures, such as ship hulls, aircraft fuselages, and other industrial applications. Where high precision in curves and bends is required, the great advantage is that the same machine allows for the production of a variety of geometric shapes, until we reach the present day where the technique of metal forming is used, which is actually a set of several other sub-techniques widely used in the automotive industry, but not only to form the various panels and parts of a car. Nowadays, the world breathes the metal sheets that have gone through the metal forming process. Cars on the road, airplanes, refrigerators, pans, washing machines, microwaves, phones, and even your computer case. Nearly everything has been shaped by metal forming, a crucial process that transformed the world. Forming is the mechanical process in which parts are made by compressing solid metals into molds, using the plastic deformation of the raw material to fill the cavities of the molds. The metal forming process is a series of techniques used to change the shape of metals, turning them into useful parts or components without removing material. Forming is fundamental in the manufacturing of a wide range of industrial and commercial products, from automotive and aerospace parts to household utensils and electronics. The process begins with large metal rolls a few millimeters thick. These rolls are later cut into specific sizes, depending on the application, and then taken to huge hydraulic presses to be shaped as desired. Depending on the application, stamping presses, for example, used to cut and shape metal sheets into body panels, can exert force in the range of 500 to 2,000 tons. For bigger, more complex components, these presses can apply over 4,000 tons of force. Forging presses, used for parts that require hot forming, such as structural components and engine parts, for example, can exert force ranging from 1,000 to 10,000 tons. Metal sheets typically pass through multiple presses in sequence to achieve the desired shape. A very good process, quite efficient, uniform, and standardized. Ed Mayer, Chief Executive Officer and co-founder of Machine Labs, says this process is very expensive because you have to build a huge and expensive factory whose design is made specifically with the final product in mind, with no possibility for changes unless you invest a lot more money in renovations first. Besides that, it has to be filled with expensive machinery designed to produce only a single model of product. If the company decides to design a new model, such as a car, it must acquire new equipment and restructure part of the factory. But that's not the worst part. The worst part, according to Ed, is that the blueprints for the product you want to manufacture have to be shared with dozens of companies that make the machinery that will produce that product. If Ford plans to make a new Ford Raptor, the blueprints for the bodywork, among dozens of other parts, must be shared in advance with the companies that will produce the presses and other machines that will be used to make the car. This problem is especially terrible when it comes to companies that deal with sensitive technology, like Northrop Grumman, which produces highly sensitive military technology for a country, such as a next-generation strategic bomber or a very advanced weapon. Boeing makes Minuteman intercontinental ballistic missiles, and General Electric produces airplane engines. Many companies worldwide face similar industrial risks because they must share blueprints with numerous machine manufacturers. The global industrial production model's uniformity and standardization greatly increase costs and create many vulnerabilities.
We're still making things the same way we did 100 years ago. To take the next leap and keep up with the digital world, we need to speed up the physical world, and that requires manufacturing to go to the next level.
And this is where Machine Labs stands out. Instead of building a gigantic factory full of large industrial presses and expensive heavy machinery, designed to manufacture only one type of part, vehicle, or product, Machine Labs uses just 2 robots to produce virtually any part you can imagine that requires forming. Instead of pressing, the Machine Labs robots push the metal sheet. To start, a metal sheet is clamped onto the support frame, and several hydraulically actuated hooks hold the sheet firmly to the frame. And it takes 2 robots working in perfect synchronization. While one robot pushes the sheet from one side, the other supports it from the other side. And for the process to actually work, the robots need to be slightly misaligned. If both touch the same region of the sheet from opposite sides, their forces would cancel out, so the sheet wouldn't deform as intended. This misalignment, which is quite small, allows for the creation of a high-tension zone where the force exerted by the robots is concentrated and the metal sheet is deformed. The robots apply enough force to the metal sheet to cause plastic deformation, a permanent shape change that remains after the load is removed. Simply applying force to the metal isn't enough to shape it as desired. Robots involve extensive science in both their movements and materials. Well, as is known, computers, just like robots, aren't very smart. They only do what they've been programmed to do, and in a repetitive way. Here, a crucial element in roboforming is specialized software and artificial intelligence developed for this purpose. And, by the way, a lot of artificial intelligence. With it, robots not only know exactly what they're doing, but also how they're doing it. It allows the robots to actually feel the material in real time, being able to apply more or less force if certain parts of the metal are more or less rigid, for whatever reason. And so the robots compensate by applying more or less force. Sometimes these adjustments happen on extremely tiny scales. AI also allows the robots to continuously learn and improve the way the task is performed, thus generating and storing large volumes of data. There are also a number of sensors that allow the robots to see in real time how the part is turning out. Adjustments can be made if needed to ensure the design turns out as expected. Not only is the robot important, but also the end effector, which is the tool that actually touches and applies force to the metal sheet. All of them are made by Machine Labs itself. These tools are made of strong and durable metals. They haven't disclosed the full composition, but they've confirmed titanium and carbides are included. They can withstand the intense forces of roboforming. And you ask, how much force? Depending on the sheet and thickness, the robots can apply 2,500 newtons or 255 kilograms of force on each side. However, that number may be much higher depending on the material. Applying the right force to metal can create shapes and figures with depth. This means that metal has a certain elasticity, which allows it to be stretched quite a lot more than we might imagine. But this elasticity has its limits. If the robots apply too much force beyond that limit, the metal can be punctured or weak spots can appear in the metal. But the complexity of the process goes even further. It's necessary for the robots to create shapes that initially stretch the material, so that the elastic deformation of the material is exceeded. That's the kind where it returns to its original shape when the load is removed. This causes plastic deformation, which is the material's permanent change.
We need to go past elastic deformation to reach plastic deformation. So, if you want to make a very shallow part, it won't work. It will just push the piece. Once you go deeper, it creates more stiffness, and you can easily go beyond the initial elasticity and create plastic deformation.
But stretching the material creates another problem, which is the reduction of its thickness, causing the final piece to be out of the specified standard. To bypass this, they use a method called restriking. And speaking of material, the robots from Machine Labs have the advantage of being able to shape any type of material, and in practically any size, from aluminum, steel, titanium, Invar, Inconel, and refractory alloys, all using the same robots. This is something unthinkable and impractical with the current metal forming industry, unless beforehand you have to invest in new, much heavier presses and restructure a large part of the assembly line. At Machine Labs, the same robots will handle various materials to make different parts. This allows companies to save millions, if not billions, of dollars on the continuous acquisition of equipment.
A factory that makes cars is an investment of $150 million just in machinery. These are 500,000 square foot plants. You also need to install stamping presses, which extend 3 stories above and below ground.
The main requirement is that the material is malleable, according to the company's website. To illustrate how roboforming is innovative, we can reference the story of Mr. 71 Blackbird, the world's fastest plane. Since the plane would be made of titanium, which was not a very common material to work with or to make planes from, special tools had to be developed, even harder ones, with diamond and tungsten carbide in their composition. In addition, specific welding techniques that could create inert atmospheres, such as welding chambers filled with argon, were necessary to create controlled environments to prevent contamination of the titanium by oxygen and nitrogen. Also, part of the factory was restructured for the new airplane's construction. In other words, the emergence of new materials or new metal alloys forces companies to completely acquire new machinery, which is terribly expensive. It becomes even more expensive with complex customizations, like a version of the airplane that lands vertically.
Ford once said anyone could have any car as long as it was black. Because I would need to change my factory if you wanted something customized, and I would never be able to do that.
Building things on the assembly line locks companies into one method of production. Therefore, making changes, such as a much more aerodynamic front end for the vehicle, or even a new color, it means halting the assembly line and making large investments. In the company's view, roboforming technology allows for versatility, flexibility, and much lower costs. So if a company intends to manufacture a completely new model of a car or multiple variations of the same one, all they would need to do is send the blueprints, that is, the digital files, to a roboforming company. And they would take care of making them, thus saving millions of dollars on building new assembly lines. Another huge area that Machine Labs focuses on is manufacturing parts for things considered obsolete. It could be from an old airplane, car, or something else. In fact, this is a multi-million-dollar market, since the original company that made it no longer exists. They scan the part or design it completely from scratch. But of course, roboforming still has major limitations and is still far from perfect. All the parts made require extensive hours of finishing and polishing. The accuracy of the technique still leaves much to be desired as well, especially for very small parts, or corners and contours. This can be especially problematic for industries like aeronautics and aerospace, where the smoothness of the material dictates the safety and performance of the vehicle, but the technique is continuously improving and evolving. The term roboforming, which was registered by them, is actually a process known worldwide as incremental sheet forming, which by definition is a sheet metal forming technique where a sheet is formed into the final part by a series of small incremental deformations. A series of sequential deformations will transform it into the final part. This technique has been tried for decades by scientists, PhD students, and multiple countries worldwide.